Okay, so finally we are here. I'm sorry, I had some problems to connect to the internet and I had to restart my computer. We were discussing the square planar complex in the last class, and thus far we have constructed the molecular orbital diagram for a square planar complex considering the sigma bonding only. So overall we arrived at this molecular orbital diagram here, and we confirmed that, well, we have 4 bonds, so 4 electrons in these 4 bonding molecular orbitals, explaining the 4 sigma bonds. And in addition to that, we have now here these frontier orbitals, which we can consider the metal d orbitals in a square planar ligand field. So now, based on that, we still have to construct the molecular orbitals under the consideration of pi bonding. So now, in this case, the situation is a little bit more complex because not all the pi orbitals of our ligand are symmetrically equivalent. So we have to distinguish between molecular orbitals that are parallel to the xy plane and those that are perpendicular to the xy plane. So let us start out again with the question, how many orbitals are there that we can use for pi bonding? So if we again use our cyano ligand as a ligand, then these are overall 16 molecular orbitals. So these are 8 pi molecular orbitals and 8 pi star molecular orbitals. Why is it 8 pi and 8 pi star? That is because each ligand has 2 bonding pi molecular orbitals, and because we have 4 ligands, that gives 2 times 4 is equal to 8. And with pi star orbitals, it's the same. Each ligand has 2 anti-bonding pi star orbitals. We have overall 4 ligands, and 2 times 4, that also gives 8 orbitals. So, like I said before, we now have to distinguish between so-called perpendicular and parallel orbitals. So because we have a relatively low symmetry, our pi orbitals are not all symmetrically equivalent. So you see here the 4 pi and the 4 pi star orbitals that are perpendicular to the xy plane. So we say that our square planar complex lies in the xy plane, and we consider any pi orbital which is standing perpendicular to the xy plane as a pi orbital which has lobes above and below the xy plane. Okay, you see here our ligands, our 4 ligands that approach the metal in a square planar fashion, and you see here the lobes of the pi orbitals that lie above and below the plane respectively. So we have 1 for each ligand, so that gives overall 4 bonding pi orbitals that are perpendicular to the xy plane, and then there are also, of course, 4 pi star orbitals that are perpendicular to the xy plane. So you see here on the right-hand side how these orbitals interact with the metal d orbitals. So you see here, for instance, this pi orbital here interacts with the dyz atomic orbital, d orbital of the metal in a pi fashion. You see here that we are getting nice and exact pi overlap, okay? And the same would also, of course, be true here for this pi orbital because it has the same orientation. So that would also interact with the dyz in a pi fashion, okay? And these two here, which are oriented in the x direction, they would interact with the dxz orbital as shown here. So this one would resemble, well, these two orbitals here, and well, these two lobes here would resemble these two. We see again, we can create nicely an exact pi overlap with the dxz orbital of the metal. Okay, so now in addition to that, we have to consider 4 pi star orbitals that are parallel to the xy plane. And you see those here. So you see again here the cyanoligand. But now you see the pi orbitals that lie within the xy plane. So for instance, for this ligand here, you have these 2 lobes lying in the xy plane. And for this ligand here, you have these 2 lobes lying in the xy plane. For this ligand, you have these 2 lobes lying in the xy plane. And for this ligand, you have these 2 lobes lying in the xy plane. So what is shown again is the bonding pi orbitals, but of course there's also a set of anti-bonding pi star orbitals that lies in the xy plane. All right. So with which metal d orbitals will these orbitals interact? Well, they will interact with the dxy orbital as shown here. So these pi orbitals here will interact with these 2 lobes of the dxy. These 2 orbitals here will interact with these 2 lobes of the dxy. These lobes here will interact with these 2 lobes of the dxy, and that pi orbital here will interact with these 2 lobes of the dxy. Okay? So you see that the parallel orbitals interact with the metal d orbitals in a different way than the perpendicular orbitals. Therefore, we have to form different sets of ligand group orbitals for the parallel and the perpendicular pi orbitals respectively. Okay, so that means that we do not get only 2 sets of ligand group orbitals for pi and pi star respectively, but overall 4 sets. Okay, so we have the 4 pi which are perpendicular. Okay. And these ligand group orbitals, if you apply again the orbital swapping method and the reduction formula, have the symmetry type A to U, EG, and B. What is it? I cannot read it anymore. B to U. And the 4 pi star orbitals that are perpendicular, they have the same symmetry, A to U, and EG, and B to U. So that means that we have 2 orbitals that have A to U and B to U symmetry, and 2 other ones that are doubly degenerated and have EG symmetry. Okay, so now here are the ligand group orbitals that are parallel. So there is a bonding set and an interbonding set, but they have the same combination of symmetries. So with the parallel ones, 1 ligand group orbital is A to G symmetry, 2 have EU symmetry, and 2 have B to G symmetry, and that applies to both the bonding and the interbonding parallel ligand group orbitals. So now we can again construct our molecular orbital diagram under the consideration of the pi interactions. Okay, so first of all, we have to be clear which orbitals interact with which orbital, so which metal orbitals interact with which ligand group orbitals. And this is shown here. In the last class, we have determined the symmetry types of our metal d orbitals, and that was B2G, EG, A1G, and B1G. So you see here in this column the symmetry types of our parallel ligand group orbitals, and here you see the symmetry types of our perpendicular ligand group orbitals. So from that it becomes clear that the 3dxy, which has B2G symmetry, interacts with the parallel LGO, which has B to G symmetry. So the EU in the A to G, they do not interact with any d orbital. Among the perpendicular LGOs, these EG LGOs, they interact with the DXZ and the DYZ. So the A to U and the B to U do not find a bonding partner with the metal d orbitals. However, we want to be more accurate. We can also say, well, we also have the 4s orbital, which has L1G. However, this 4s orbital will not find a bonding partner with any of the pi ligand group orbitals, okay, because we do not have any LGO with that symmetry. However, the PZ orbital, which has A to U symmetry, can interact with the ligand group orbital, which has the same symmetry, which we just previously determined. So the PX and the PY orbitals have EU symmetry, and that means that they're able to interact with the EU ligand group orbitals, which are parallel. So overall, the only ligand group orbital that cannot interact in pi fashion with a metal frontier orbital is the B2U ligand group orbital, which should remain truly non-bonding with respect to pi bond. Okay, so now we can construct our molecular orbital diagram accounting for both the sigma and the pi interactions. Okay, so we can again plot our metal frontier orbitals here on the left side and assign symmetry types accordingly, which is the way we have already done in the last class when we considered the sigma bonding only. And now on the right side, we plot all the LGOs that can make bonding interactions with the metal frontier orbital. So these are, of course, the sigma LGOs, which we have already considered in the last class. But now, in addition to that, we have the pi LGOs, okay, both the parallel ones and the perpendicular ones. So the bonding pi LGOs, they are filled with electrons, okay. But now, in addition to that, we have also the interbonding LGOs to consider, and these are energetically significantly higher in energy and do not contain any electrons. Okay, so overall, from this picture, we would see that our ligand, which is in this case our cyanoligand, would be primarily a pi donating ligand, and the pi accepting properties would be very weakly expressed, just because the pi star orbitals are significantly further away from the metal orbitals in comparison to the bonding pi LGOs. Yes.
How do we differentiate which is the perpendicular, which is the parallel, in the pi LGOs? So how do we know which one's going to be like? Just like I know, like visually, we know which one's, but in like the diagram, how do we differentiate between parallel and perpendicular? Or is it because like it's the same number, there's no difference?
If you had no,
yeah. So
if those are closer to the metal frontier orbitals.
Okay.
Is that your question? Or did I misunderstand your question?
But with the last slide, we have, the parallel ones and this one. So, like, will we be able to differentiate from our diagram, which is the parallel and perpendicular from here?
Right, we see here the symmetry designations.
Okay.
So from the symmetry designations, you could read which is parallel and which is perpendicular.
Oh, got it.
Yeah. Okay, then let us start constructing molecular orbitals, and we only need to go through the symmetry type step by step and construct the molecular orbital diagrams. So for instance, we can start with the symmetry type A1G. So we see that we have here two orbitals, metal frontier orbitals with that symmetry type. When we look at the ligand group orbitals, we see there's only one ligand group orbital that's symmetry type, and that's one of the sigma ones. So we just combine these three to form three molecular orbitals. So one we would expect to be bonding of low energy, one to be interbonding of high energy, and one should be approximately non-bonding, having intermediate energy. All right, then we can, for instance, go to the B2G. Okay, so there's one metal d orbital which has B2G symmetry. We see that we have also one pi ligand group orbital that has B2G symmetry, which has similar energy. There is, and this is actually not shown, and maybe I just remove this bar here. Also here, one B2G orbital, which has the same symmetry. Okay, so now we can almost neglect this one here, and the bonding interactions will be primarily between this one and that one because they have much more similar energy. However, we should also write this orbital here still into the molecular orbital diagram, but it won't change much in energy because it hardly interacts with this B2D because it's energetically very far away. All right, we can go to the next symmetry type. So for instance, we can go to the symmetry B1G. We realize one d orbital has that symmetry type, and there is one of the sigma LGOs which has that symmetry type. Okay, there are no pi LGOs that have that symmetry type, so no pi interactions coming from that symmetry type. So that means that we have only two, so we construct a bonding molecular orbital and an interbonding molecular orbital that has lower and higher symmetry respectively. Okay, then we are done with our B1G. So next, for instance, we can consider the EG orbitals. So we see these d orbitals have EG symmetry. We see that there are two bonding pi orbitals that have EG symmetry. And here also these interbonding pi orbitals which have also EG symmetry. Okay, again, these EG orbitals are fairly way up in energy, so not much interaction from them. So we have primarily here this bonding EG and these interbonding EGs, okay, at lower and higher energy respectively. However, we also need to write, to make it complete, these two into the molecular orbital diagram, but again, they don't change much in energy because they only very weakly interact. All right, so our next symmetry type can, for instance, be the EU symmetry type. So we have a lot of EU orbitals. So the 4p orbitals have, two of them have EU symmetry. So we have sigma LGOs that have EU symmetry, but we also have pi LGOs that have that symmetry. So in this case, we get both sigma and pi interactions for this symmetry type. The respective molecular orbitals have both some sigma and pi influence. So overall, we have 1, 2, 3 pairs to consider. So again, this pair here is energetically way out. So we just write it with approximately the same energy. So the interactions will be primarily between these EUs and these ones here. So that gives overall 3 pairs we can approximate. That one will be bonding, one will be anti-bonding, and the third one will be approximately non-bonding, being of intermediate energy. Okay, so you see the bonding here, the approximate non-bonding here, and the anti-bonding here. Okay, so what's left? Well, there are also the A to U orbitals left. So one 4p orbital has A to U symmetry, and there is this pi LGO, which has A to U symmetry, as well as this one. Again, this one here doesn't do much because it's energetically far out. The interaction will be primarily between this 4p and this A to U here. That creates this bonding one, this anti-bonding one, and well, that one here remains almost unchanged in comparison to that one, because the influence, the contribution of this A to U is small because it's energetically too far away. Okay, now have you forgotten something? I think we have them all now except this B2U pi LGO, which does not find a partner at all. Yeah, there's no metal orbital with that symmetry type. So this B2U remains non-bonding, and that B2U also remains non-bonding. Okay. Wait a moment, there's also another one. Yeah, so by the way, also this A to G and this A to G remains non-bonding. Yeah, because it also doesn't find a partner, there's no A to G. But it also applies to the B to U here. Okay, so we have this one B to U as well as that B to U. And now we have considered them all. Okay, so now you see our molecular orbital diagram that we have created looks quite complex. And if we just looked at it, we may have been overwhelmed because it looks so complicated, but you see, if you go through the symmetry types step by step, you can construct it fairly rationally, and with that rational approach, you can even understand and construct fairly complex molecular orbital diagrams. Of course, with our qualitative considerations, there would be relatively many uncertainties with the relative energetic order of these orbitals, but if such a molecular orbital diagram could be presented to you, you could still rationally understand how it has been constructed. So we still have not considered the electrons, so we still have to fill the electrons into our molecular orbitals. So we have these 4 sigma electrons from the sigma LGOs, and in the last class we already filled them into these 4 bonding LGOs here, make now 4 sigma bonds. And we could therefore say, well, these are our sigma bonding molecular orbitals. Okay? So now in addition to these electrons, we have these 8 plus 8 is equal to 16 pi electrons. And we must occupy now the molecular orbitals of the next higher energies. Okay, so 16 electrons fit into 8 orbitals. So the next 8 orbitals would be considered our pi molecular orbitals. Okay, so that fills the one B2G, the one EG, the other one EG, the A to U, the first 2 EU, the second 2 EU, the B to U, and the A1G, and I believe these are 16. Okay, so these would be our pi bonding molecular orbitals. Okay, so now we have considered all the ligand electrons, and any existing metal D electrons would now go into the next molecular orbitals. Now, how many of these are being filled depends on how many metal electrons we have. So remember, we have learned that D8 metal ions, they like to make square planar complexes. So let's just work with this electron configuration in 8 d electrons that would then fill the 2b2g, the 2eg, and the 2a1g. So this one here would be our highest occupied molecular orbital. So this one here would be our lowest unoccupied molecular orbital. So overall, we could say that these 5 orbitals would be our metal d orbitals in a square planar ligand here. Okay. So now with this picture, we would also understand again why the d8 electron configuration likes to make square planar complexes, because it allows to fill these orbitals here, which have relatively low energy, but this 2AU is actually strongly interbonding. It's beneficial not to be occupied from an energetic standpoint. You have also previously learned that square planar complexes tend to be 16 valence electrons complexes, violating the 18 electron rule. And if we count our electrons, excluding the pi electrons, which are not accounted for in our electron counting method, then we will arrive at 16 electrons. You can just count them. So it's basically these 8 here, plus these 8 here in addition. Okay, and now we understand again why the 18 electron rule is violated for the 16 electron complex. If we added 2 more electrons, they would have to go into this 2AU orbital, which is energetically significantly higher than that 2A1G orbital here, and that would be energetically very favorable. Okay, now we have explained 3 shapes using our ligand field theory: the octahedral case, the square planar case, and the tetrahedral case. And you see that the ligand field theory works well for all the different shapes, and it can explain both magnetism as well as electronic spectra. However, you have also seen it's the most complex bonding theory to use. So whether we want to use it or not just also depends on how much information we need. If it's just basic information, perhaps just the valence bond theory or the acoustic field theory would be enough. But for more detailed information, we would need to construct the molecular orbital diagrams. Okay, so this is now the end of the chapter about bonding theory. So now what I would like to do is start a new chapter which is about electronic spectra. So this chapter now builds on the previous chapter. We are now having a closer look at the optical properties of coordination compound, which can be explained by, well, the bonding within the compounds. And we'll see that even our ligand field theory is often not sufficient in order to explain the experimental optical spectra. We have to take additional considerations into account. So nature makes it even more complicated for us than we might have thought. All right, so now where's my Zoom meeting? Where did my Zoom meeting go? I just launched it and I hope it just goes to the same meeting again. Okay, so here we go again. Still the same meeting. There's still have the recording. Yeah, it probably went away because I removed the bar over there. All right, let's go here. Then I'll start this. Okay. Let us consider an octahedral nickel complex, and let us see how well the ligand field theory can actually explain an experimental absorption spectrum, which would be characteristic for the optical properties of the complex. So here we have an octahedral complex. It's a nickel. It's a hexa aqua nickel 2+ complex. So according to that, we would have octahedral ligand field. So we would have our T2G orbitals and the EG orbitals, and we would have 8 electrons. So 6 of these would be in the T2G, and 2 of them would be in the EG. So now what optical property would we expect for this complex according to this picture? Well, we could say we could promote one of the electrons in the T2G into the EG orbit. So that would, if we measured an absorption spectrum, then that would correspond to one absorption band. And the position of the absorption band would be characterized by the size of the delta O. So now we can experimentally measure, and what we will find is that the absorption spectrum of this complex looks a lot more complicated than ligand field theory would predict. So instead of just one absorption band, you see that there are at least 3. And if you look closer, then you see that this could be shoulder here, and well, that peak is actually just 2. So instead of just one absorption band, we see multiple absorption band, and that is inconsistent with what ligand field theory predicted. And the lesson from that is that the electronic structure in a complex is even more complicated than what ligand field theory would predict. And why is that so? This is because any molecular orbital that we construct is basically a one electron function. So these molecular orbitals, they do not take into account electron-electron interactions. Okay, stemming from electrostatic repulsion and magnetic interactions between the electrons. And therefore, the ligand field theory still gives us an oversimplified picture. And in order to get an even more accurate picture, we now have to take into account electron-electron interactions. Okay. So now let us illustrate what that means by an example. So let us assume a T2 ion in an octahedral complex. So for instance, we could have one electron in the dxy orbital and another electron in a dxz orbital. Okay. So now, what could happen as we excite our complex and promote one electron? Well, we could, for instance, move our electron from the dxy to the dz square orbital. Then we would have one electron in the dxz and one electron in the dz square. However, we could also do the excitation somewhat differently. Okay, so instead of promoting the dxy electron, we could also promote the dxz electron into the dz square orbital. Okay, so now according to our ligand field theory, both of these states would have to have equal energy. Okay, but that is only the case if you do not account for electron-electron interactions, okay? Namely, the interactions between these two electrons. If we account for the electron-electron interactions, then the energy of this state here, it's actually a so-called microstate, an example of a state, would be different in comparison to this microstate here. Okay, because the electron in this case interact differently than in this case. Okay, so this becomes fairly easily understandable from the geometric interpretation of these two microstates. Okay, so you see here a DXZ orbital. Okay, and you see here over there a DXY orbital, and you see that they have different orientations. Okay, the DXZ orbital is oriented in the Z direction, while the DXY orbital is not. So we can add our dz square orbital, in which the other electron is being located, to that picture, and the dz square orbital has, of course, a strong Z component. So, taking this into consideration, it becomes plausible why the electrons in this case interact differently than in that case. Okay, and that leads to different energies for these two different microstates. Okay, that belong to the same state, meaning that, well, one electron is in a T2G orbital and the other electron is in an EG orbital. Okay, so now in order to correctly predict our electronic spectra, we would need to calculate the energies for each and every possible microstate for that particular electron configuration, which is in our case a D2 electron configuration. Okay, and then group microstates of the same energy together. And then the number of groups would determine the number of possible electron transitions, which should then be consistent with an experimentally measured electronic spectrum. So now a group of microstates that has the same energy is called a term. So our task is basically now to find all the terms that belong to a particular state in a particular electron configuration, and then the energies of these terms would define the electronic properties of our, or the optical properties of our complex. All right. So now, how do we approach this? So, in order to approach this, we need to consider both the electrostatic interactions between the electrons as well as the magnetic interactions. So the electrostatic interactions are being determined by the quantum number ML. Okay? So this is called the magnetic quantum number for a single electron, which can vary between -L and L. Yeah, where L is the orbital quantum number. All right. So now, how do the magnetic quantum numbers of several electrons interact quantum mechanically? And quantum mechanically, they just add. Okay. So therefore, when we have multiple electrons, then the number of electrons defines, well, having particular quantum numbers, ML defines the overall quantum number ML for a particular microstate. Okay? Okay, so now ML is called the total orbital angular momentum for all the electrons. In our previous example, it would be 2. Okay, so now the maximum value ML can adopt for the different combinations of electrons is called capital L. So capital L is the total orbital angular momentum quantum number, and has a particular meaning because it defines the name of the term. It also defines the number of microstates that belong to a particular term. So it defines the number of microstates that have all a particular energy, the same energy. Okay, so the number of microstates that belong to the term due to the total orbital angular momentum quantum number is 2L plus 1. Okay, so this is because ML can vary between minus L and plus L. Okay, so this is the number of ML values that we can have for a particular combination of electrons. All right, so now in addition we can have the interactions of the spins. Okay, so an electron can either be spin up or spin down according that defines its quantum number ms, and that can either be plus a half or minus a half. So now we have multiple electrons, the spins just add up to give a total spin quantum number. Yeah, that is then called ms, and the maximum ms value which is possible defines then a capital S, which is total spin angular momentum quantum number. Okay, so again, this number is important because it defines the number of microstates in the term due to the spin, which is 2s plus 1, and it defines the overall spin multiplicity in a term. Okay, so 2s plus 1 is also called the spin multiplicity. So the overall microstates that belong to a term is then, well, 2L plus 1 times 2s plus 1. Okay, and the quantum numbers capital L and capital S then also define the overall term symbol. So the L value defines the letter for the term. So when L is equal to 0, we call it an S term. When it's equal to 1, we call it a P term. When it's L is equal to 2, it's a D term. And when it's 3, it's an F term. So we assign the letters according to what we know from the orbitals. So remember, for an orbital quantum number, L is equal to 0, we have an S orbital. When L is equal to 1, we have a P orbital and so forth. And here, basically, we have the same system. For capital L is equal to 0, we have an S term. For L is equal to 1, we have a P term and so forth. Okay, so now in front of that symbol, we write the spin multiplicity, which is given by the number of microstates in the term because of its spin. Okay, which is just given by the formula 2s plus 1. So that defines the spin multiplicity. Okay, so let us stop at this point.